Okay, hi everyone. Hope you had a good holiday. It's strange to have a holiday so close to the end of term. Okay, let me. Okay. Strange. Why is it doing this now? All right. Okay, so in this last week, I want to introduce a new idea, the last idea, which is about, well, it's a kind of combination of two things that are both associated with the name Feynman, named after Richard Feynman, one of the most famous physicists of the 20th century. One of them is the Feynman path integral, which is a kind of, it's a different way of understanding the relationship between classical and classical mechanics and quantum mechanics. It's a yeah, it's a kind of a very powerful heuristic which is used for quantization, for relating the classical and the quantum world. And related to that is a diagrammatic method for making computations in perturbation theory. So I'm actually not going to talk about the path integral today. I'll leave that for the last class on Friday. And what I'm going to focus on today is just this perturbation theory calculus. So this is just purely this is a kind of purely mathematical technique for computing certain types of integrals, and it turns out to have a diagrammatic formulation, which I'll try to explain. I'll try to explain where the diagrams come from. Okay, so to do this, basically, I just need to teach you how to do certain integrals, and then what they mean, or how to interpret them, and the so some integrals. So the general topic is perturbation theory via some finite dimensional integrals. Oops. Via diagrams. Okay, so it's basically going to be a toy model which motivates the idea that we should be able to do perturbation theory using diagrams. Okay, so so the first thing we need to do is figure out how to do some easy integrals. So the first integral, I'll just write it the way it normally would be written, e to the minus x squared dx, like this. Okay, so what is this integral? Well, you could think of it as an integral along the real line. So we have the real line. We have a function on the real line, and it's a famous Gaussian function, and we're basically computing this this area. Right? And the famous integral. I hope you learned how to do this integral at some point. The way that we typically teach people to do this integral is to square it. And if you square it, then you get the integral of e to the minus x squared dx multiplied by the integral of e to the minus y squared dy, if we use a different dummy variable. Then you could think of that as an integral over R2, the xy plane, the double integral of e to the minus x squared multiplied by e to the minus y squared, right? And that's e to the minus x squared plus y squared, using the property of the exponential. So it's really an integral over the plane of e to the minus r squared, where r is the radius, right? And then you can break it up as a polar, in polar coordinates, where you do first you do a theta integration, and then you do an r integration. And if you do that, you'll get as a result you'll get pi. So the square of this integral is pi, and so this integral is square root pi. I'm not writing down all that derivation because you should have known this. Okay, so let's take this as a given. The next one is similar. Is this one, right? Anyone have a quick answer to this?
I don't actually remember exactly, but is it square root of 2 pi over a?
Yeah, it is square root 2 pi over a. And how did you calculate that so quickly?
Well, I remember at least the over a part from previous classes, but then I couldn't remember where
memory.
Go.
You used memory.
Yeah.
Okay, so the way you should do it is by we're just rescaling x. If you rescale x to get rid of the a, you're going to be integrating. You're going to change the integration measure, right? This will get a 1 over a, and if you do the same thing with the 2, then it'll become a square root 2 on top. So by rescaling x, by doing a simple change of variable, we get square root 2 pi over a. Okay. Now, next one. Okay, and here's the perturbation. Well, the first perturbation that we're going to see. This one is not an important perturbation, but it is a slight modification of the one above. Okay, and the way that we're going to compute this one is by see, the problem is this is not of this form, but I want to make it into this form. So the way to make this into this form is to complete the square. So I'll get so I completed the square by adding this constant, and that reproduces this, except that it produces a third term, namely it gives like minus a over 2 times j squared over a squared. Okay, and so then because it introduces that extra stuff which is not present here, I need to remove it, and so that undoes the problem. So this product is equal to this. Okay, this is just a constant, so it just comes right out of the integral. And this one is exactly of the same form as this. It's just that it's a shift of the x variable. So we're just using a change of variable where we're shifting the x variable, but we're integrating over a domain which is invariant under translation. So that change makes no difference to the integral. So the value of this integral is exactly the same as that. So what you end up with is the square root 2 pi over a, same result as before, multiplied by a factor, which is e to the j squared over 2a. Okay, so very simple. We can bootstrap ourselves from this answer through some changes of variables to get this answer. Okay, now, okay, so this is an interesting fact. We're going to use this identity in a moment. Okay. So second part. So this is now the perturbation. So the perturbation is going to be this. I'm going to integrate e to the minus 1 half ax squared plus 1 over 3 factorial b x cubed dx, and the parameter, the small parameter, which means just the expansion parameter or the sense in which it's a perturbation, is b. And we'll take b to be a real number, let's say. Okay, so now I'm doing a more complicated integral. I'm integrating a Gaussian which has been multiplied by something which is not a Gaussian, but rather it's e to the cubic power. Okay. This is a perturbation of the original result, so we should expect, I suppose, we should expect maybe that if b is small, that this result should be close to, let me call this I of b, or actually let me call this z of b. So this is a function of b, and I'm interested to know how does this answer get modified when I turn on b, when I turn on the perturbation? Is it clear, the question that I'm asking? Any questions about the setup?
Doesn't this interval not converge? Or
say it again?
Doesn't this integral not converge?
Yeah, good question. So why do you say that?
Well, for example, if b is positive and x gets very large, then the exponent will be positive and we'll just keep getting something that goes to infinity.
Yes.
Our function doesn't go to 0.
So therefore your question becomes a statement, the statement being?
This integral does not converge.
Right. Okay, that would be a correct statement if I told you what the integration domain was. And you're assuming that the integration domain is?
The real line.
Yeah, so that's a correct statement. If you integrate over the real line, this is a divergent integral. And so this is mathematically not defined. And it's also physically not defined. It's just not defined. There's no difference between mathematicians and physicists at this point. So this is this diverges unless we choose a contour of integration which is good. So what is a good contour? Well, I don't want to spend too much time on this, but we need to go to the complex plane. So we're now going to go to the complex plane, and we're going to use x as a coordinate on the complex plane. So we're going to now view our fields, or rather our variables x, right, as the variable x, we're going to view it as a complex variable. And we're going to do an integration on a contour c. And what we want out of this contour is that it should be as good as this contour. We want exponential decay along the ends of the contour so that the integral will be absolutely convergent. So how can we do this? Well, when we're looking in the complex plane, what is the problem? The problem is that for large x, this term dominates the integrand. Okay, so let's investigate both. Let's investigate both parts of the integrand. There's this part of the integrand, the Gaussian part, and then there's the non-Gaussian part. Now, the Gaussian part, if you let x be positive and large, so let me assume that a is positive here. So if we let x be large and positive, that's a good region. My integration contour. Sorry, let me just organize. I need to investigate both terms. So let me do this. I'm going to need 2 copies of this. Let's look at the behavior of this polynomial. So this polynomial, when x is large and real, positive real, right? This polynomial is negative, which means that the exponential is decaying rapidly, which means that it's a good area out here. And if x is negative, then it's a good area as well. For large x negative, this polynomial is highly negative and the exponential is close to 0. Okay, so that means this is the good region where we can take a contour. We can take our integration contour, and if it limits to the green region, then we're going to be okay for absolute convergence for the integral. Now, how big is this green region? Well, it actually, if I go at a certain angle, like e to the I theta, then this green region is perfectly good for a good angular region, for a significant angular region. The same statement will hold, that the real part of this polynomial will be negative. Okay, but at some angle, namely 45 degrees, okay, then what happens is that the square, let's say if x is pi over 4, e to the I pi over 4, then when I square it, this will be imaginary, right? And that will be a boundary point. So that means that the real part will be 0, and this thing will be oscillatory along here. So there's a bad locus, or there's a kind of warning track here where the integral becomes oscillatory. And then if you go to infinity, if x goes to infinity in the upper or lower quadrants, right, then we're going to have exponential increase of this quantity, right? So the contour needs to be chosen so that you can do whatever you want with your contour as long as the beginning and end are in the good region at infinity. Okay, so this is the key way to define such integrals. You need to make sure that your integral contour begins and ends in a region at infinity where the exponential is decaying rapidly, not increasing like it would be up here. Okay, and along the orange, the yellow, that's exactly the separatrix, the direction where once you cross that direction, it goes from good to bad. Okay, so this integral, this Gaussian integral, sorry, let me close the window. So, right. So the Gaussian integral actually is well defined for any contour that limits to the green regions and gives the same result. So it doesn't depend. You can wiggle the contour. It doesn't matter because of Cauchy's theorem. So you see that there's a yeah. Now what about this polynomial? This polynomial is cubic. So that means that as we go around the circle, right, the real part of the phase of this polynomial will oscillate, not it won't be like this where it goes up and down 4 times, or really in terms of directions. So this is cubic, so it's going to move at a three halves similar pace. So what's going to happen is you'll have if x is positive, that's bad. And where will the bad region reappear? It's going to reappear exactly if you multiply by a cubic root of unity. So if you multiply by a cubic root of unity, there's going to be another bad region here, and there's going to be another bad region here. And the separatrix will be exactly this. So we're going to have a bad region out here, another bad region out here. These should all be the same angle, and a bad region out here. And then the other regions are good. This is a good region, this is a good region, and this is a good region. Okay. So this is given by a pi over 4 angle, and this is given by pi over 3 angle. Okay, and so what does this mean? This means that in order for, like, let's say the ax squared was not there, and I only had this term. If I wanted to define the integral of e to the bx cubed, right, then the type of contour that I should pick, well, I mean, one possibility is that I could pick a contour like this, because it begins and ends in the good region, and there's exponential decay at both ends. And this would be a well-defined, absolutely convergent integral. Okay, another possibility is that I could go like this, C prime. Or I could go like this, C double prime. So there are 3 possible choices of contour to make this integral, if I didn't have the x squared, let's say, to make this integral well defined. Okay, and these are not linearly independent, because you can see that if I go from here to here, and then here to here, and then here to here, right, then I'm basically going around in a circle, and you can contract that. And so the sum of the 3 integrals along these 3 contours is 0. I'm just using basic complex analysis here. So really there's only 2 linearly independent integrals when we have a cubic. And in general, depending on the power of the polynomial, you're going to get n plus 1 or d plus 1, d minus 1 linearly independent integrals, okay, which are analogous to the Gaussian integral. Now, okay, any questions about this? So sorry, let me say the final step in step 2, and then I'll ask for questions. So if we want to choose a contour for this integral, we need to make sure that the contour is good for both parts of the integrand. So what we could do is we could just choose a contour, like, let's say a contour like this, which goes from here, which is good for both, and which limits, let's say, let's see. So this is pi over 3. So there's a little bit of room. Sorry, where's the room? pi over 6, I'm sorry. Yeah, pi over 6. Sorry, no one corrected me. So that means there's a little bit of room here, which is good for the right and also good for the left. And so that means that if my contour goes in that region, then at infinity, it's going to be good. I could also go from here down to here, okay, which is actually the most typical choice in this case, but it doesn't matter. The point is that there are contours which are good for both terms. Which is between pi over 6 and pi over 4. Okay, as long as we do that, this will be good on both ends. And it'll be rapid exponential decay on both ends, and it will be an absolutely convergent integral. So that is the contour C, and that is how we define this integral mathematically. Any questions about this?
Are they just going to be cubic roots of unity, multiples of each other?
I don't know what you mean by they. Who are they?
We have 3 integrals, which are 3 numerical, they're 3 complex numbers. To get from, if I take the ratio.
Well, if you're asking me whether this integral has a Z3 symmetry, the answer is no. But if the A wasn't there, then it would have a Z3 symmetry, and the contours, what would that mean? It would mean that if you integrate along one contour or along its rotation, then you would get the same result. You just need to make sure that the integral has the symmetry that you're asking about. Okay. So anyway, that's what this integral has a perfectly well-defined meaning. This is a well-defined. This means that z of b is an analytic function, except let's say for generic values of a and b. Okay, so there might be some singularities which we need to investigate, but at least we can see that as long as it's, you see, like if we define z of b according to this contour, by integrating along this contour, then as long as we modify b, sorry, let me rephrase this. Let's say, suppose a is fixed, okay, and b is chosen to be on the positive real axis, then this will be an analytic function for b sufficiently close to b0. Okay, the reason that I say that is that this integral is defined along a certain contour. If we modify b a tiny little bit, this contour will still be good. Okay, and so what we're doing is we're doing a single integral of an analytic function along a single contour, and we're just looking at how it depends on a parameter inside the analytic function. So that means that this z of b will be analytic. But of course, if we let b move too much, then what will happen is that this contour will no longer be good. Okay, because the positioning of the of these lines will depend upon B, especially if we move B off of the real axis. Okay, then the places where the good and bad regions will shift. Okay, so at least we know that Z of B is some kind of analytic function of B. Okay, so so the main question that physicists, so in physics, we 1/2 a x squared is the analog of the free particle Lagrangian, and the b over 3 or b over 6 x cubed, this is the interaction term. This is because we only have one variable. This means that it's an interaction of x with itself. Okay, so for now, just think of it as an analogy. I'll try to flesh it out a little bit on Friday. Okay, and this z of b, this is the so-called partition function of the interacting theory. And z of 0 is the partition function of the free theory. Okay, and so the terminology partition function is taken from statistical mechanics, where you organize the information. So in quantum mechanics, you have a system, you have some kind of quantum system, and then you compute various observables. You compute expectation values of observables. And in statistical mechanics, you compute probabilistic expectation values of certain events. Okay, and the idea of the partition function is that the partition function tells you somehow, it gives you an overall description of the energy of every microstate. And if you know the partition function, then you can deduce all of these probabilistic outcomes just by doing mathematical manipulations on it. So this z of b function is like the ultimate goal of the computing in quantum field theory or statistical mechanics or whatever, because it is the generating function for all physical observables. So it is the ultimate goal of QFT or statistical mechanics to compute z of b. Okay, that's why mathematicians like to make fun of physicists and say that the only thing that physics is that it's the evaluation of integrals of the form g of x e to the minus f of x dx. If you know how to do all these integrals, then that's what physics is. So of course, that may be true, but you shouldn't take it as an insult. Okay, so the idea is that that we want to compute this integral. Okay, perfectly well-defined integral. The problem in quantum field theory is that it's not so easy to understand how to choose the contour. And even once you know what the contour is, it's difficult to see that the integral is absolutely convergent, and it's most likely not the case anyway. So it's a huge mess, but at least in this toy model, we have a well-defined integral that we would like to compute, okay? And the way that we're going to compute it is by perturbation theory. So let's compute this integral dx. Okay, so the way that we're going to compute it using perturbation theory so perturbation theory is a glorified name for expanding it in power series. Something in power series. Okay, and what we're going to do is expand this in power series. The interaction. Okay, so how do we do that? Okay, and then we're going to put here, this is e to the b. So this is going to be, I'm going to expand using the Taylor series for the exponential. So this will give me 1. Okay. Now, okay, so I don't want to expand, the technique is like this. I don't want to expand the first part. And the reason is because, the reason should be clear now, because now that we have this and this, then this term, I can integrate it. Then this is a well-defined integral, right? If I didn't have this here, I wouldn't even be able to integrate 1 along this contour. So, and then the same thing goes for this. This is a polynomial function, goes to infinity as x goes to plus infinity and minus infinity. So this is very large, but it's getting killed by this Gaussian, right? And so that means that this integral will be well-defined as well. Okay, so the whole idea is that now term by term, this integral exists. Okay, and so term by term, we now exchange the integral along C with the sum. This is illegal to obtain a series of well-defined, I said series, and then that idiotic phone replied. Incredible. I said a series. And it responded again. Very good. Oh, God. All right. To obtain a series of well-defined integrals. Okay, so this will be a sum of integrals along C of this Gaussian term multiplied by a prefactor, which is a polynomial. So I get bx cubed over 3 factorial to the k over k factorial, sum over k. Okay, so this step is illegal because you need a certain type of convergence in order to get equality. And so this is only formally equal. And I'm going to try to explain what the mathematical meaning of this statement is. So mathematically speaking, this is what's called an asymptotic expansion of z of b as b approaches 0 in r in r greater than 0. So there is a notion of asymptotic expansion of a function at a point along a direction. That's a mathematically well-defined notion. You need a function, you need a point, and you need a direction. Okay, so that is the okay. Now the thing is that this function here's the key point. The key point is that the function z of b is not analytic at b equals 0. Okay, it has a singularity there. Nevertheless, it doesn't mean that we can't compute the asymptotic expansion at that point. So computing asymptotic expansion at a point does not require that your analytic function is analytic at that point. Okay, so you can do an asymptotic expansion of an essential singular a function with an essential singularity at a point. You can do an asymptotic expansion in a specific direction, because in some directions the function is well behaved. In other directions it might be going to infinity. But in those directions where the function is well behaved, it is possible to do an asymptotic expansion. Okay, but so I'm just telling you the truth about what is going on. But this computation is perturbation theory. So to compute this, so we'll define z hat b Yeah, so we're going to compute this. Right. This will be computed. So in perturbation theory is the computation of this formal series. This is a power series in with complex coefficients. And each term will be obtained, each coefficient of the series will be obtained from a finite sum of contributions, each from a Feynman diagram, which is a graph. It's basically a type of graph. Okay, so it's a powered series. We need to figure out each coefficient. When you're trying to figure out one coefficient, you need to sum a finite number of diagrams. And each of those diagrams is going to contribute something to that coefficient. Okay. Now, okay, staring at this example, it's clear what we need to figure out. So so I'm going to develop this in several steps. I'm not going to be able to finish today, but the first step is that we need to we'll need to compute something like this, x to the k e to the minus 1/2 ax squared dx. If we know how to compute these, right, then we'll be able to compute all of these, because this is just some constants plus an x to some 3k whatever. And so this is the basic type of integral that we want to be able to compute. Okay, so this is not on our list yet. So far, I told you to compute these, but I didn't put anything in front of the exponential. Okay, so we need to compute this. And so what is this? So it's an integral. So what's the contour? Well, the contour we said was chosen to be in the green region at both limits. But now that we're computing this, because this is good on such a big contour, such a big region, we can basically just take this one to be from minus infinity to infinity. That's not a problem. So this is the quantity we want to compute. Okay, and I'm going to deduce this from our little lemma here, this one. Okay, so just recall this. How is this going to be helpful? Well, this thing here, this, let me move this a bit. What is this? This is z of b, but it has another variable j. Oh, I'm sorry, z of, this is, let me call this, let me just call this f of j. It's a function that depends on j. I mean, it depends on a as well, but we already dealt with the dependence on a. So, and of course we computed this. It's just equal to this. It's an exponential function of j squared. Okay, but look at how it looks in the integrand. So if I were to if I were to take the derivative with respect to j, right, then what would happen in the integral? It would take an x down and put it in front. Okay, so if I take the derivative with respect to j, that's going to bring down an x. If I take the derivative with respect to j again, it's going to take down another x. Okay, and some other stuff too. But so in that sense, I'm going to get the integral of x times this thing by taking the derivative with respect. So if I take, let's say, the derivative with respect to j, right, this is going to be x e to the minus 1/2 ax squared plus jx. So I'm almost there. I just need to set j equals to 0 now, because then this term will go away, and I'm going to get the integral that I want. Okay. And okay, and right, and guess what the answer is to this? Well, I can compute it, because this is d by dj of, I already computed the answer of what f of j actually is. Right, well, what's going to happen? I'm going to get, the j derivative is going to give me j over a in front times e to the j squared over 2a. And then I'm going to set j equal to 0, and I'm going to get 0. Okay, which is not surprising, because this is an odd function and this is even. And so, and my integration domain is invariant under the Z2 involution. So it's obviously the right answer. Okay, but I'm just demonstrating how you would get these things. So then what about the integral of x to the 2k, even powers of x? That's the one we really need. E to the minus 1/2 ax squared dx. What is this going to be? Well, this is going to be d by dj to the 2k. I'm going to differentiate 2k times this f of j, and then set j is equal to 0. So let me just do the k equals 1 case just to show you how this works. So if I have d by dj, oh well, okay. So let me do this again. So this is like a inverse j squared over 2. This is what f of j is, right? It's e to the j squared over 2a. Let me forget about the prefactor. This is the key point. So we're taking the 2k derivative of this and then restricting to j equals 0. Okay, so if you think about what this is going to do, so if you apply 1 d by dj, so after 1 d by dj, what are we going to get? We're going to get a inverse j times the same thing again. So that's after 1 d by dj. So let me just draw it as a kind of picture. Okay, so if you apply d by dj, you're going to get this. So what did it do? It brought down a j, and it always an a inverse together with it. Now, the next application of d by dj is going to give you two terms. Okay, so the next d by dj, the d by dj is either going to act on the front part, and it's going to kill the j that this guy brought down. This guy brought down a j, and then this guy is going to kill it, and I'm going to get a inverse e to the a inverse j squared over 2. But the other possibility is that the d by dj could bring down another j, and then I will get a inverse j squared times e to the a inverse j squared over 2. And I'll get a sum of these two terms. So this is after one step, and this is after the second step. Now, so this term is good because, because if I set j equals to 0 now, this will be 1, and I'm just going to get a inverse. And the second one is just going to be 0. Okay, so you can see that why. So this is telling me that this tells me that our first non-trivial result is that x squared e to the minus 1/2 ax squared dx is equal to square root 2 pi over a multiplied by a sorry. Yeah, is times a inverse. Let's see, f of j, I just want to make sure. Yeah. And this expression, and so if we want to get rid of, so we'll define the expectation value. Oh, I should stop, but let me just finish my thought. Define the expectation value x squared to be the integral x squared divided by the integral ax squared dx. And this is just a inverse. Okay. And this is a very elaborate way by the way, of inverting a number. If you didn't really want to invert it, you could just compute this integral and divide by the integral, and you would get A inverse. It turns out that you can generalize this, can use the same technique to invert a matrix, actually. You could compute the matrix inverse by computing a bunch of these Gaussian integrals. You would need, for x to be a vector, for this to be a bilinear form. And if you use an integration over Rn with a bilinear form, you're going to get the inverse of that matrix. So, okay, so this is the key calculation. So on Friday we'll just push this further, and we'll see this has a, yeah, we'll push this further and continue with our integrals, and yeah, to be continued. Now we have office hours.
Do we have class on Friday?
Yeah, why not? Isn't that the last day of classes?
Oh, my bad. Okay, I thought it was 8. My bad.
It's okay. Okay, bye everyone.